gravitational wave from phase transition. Graham, are you there?
Yes, I'm here. Yes. Can you hear me?
Yeah. Thank you. Yeah. So this control is here.
Okay. Yes. So we had a few questions in the chat, although most of those seem to be resolved. So perhaps it'd be useful to open the floor up on each of the topics one at a time. We had some very nice topics come today, and I think we can categorize them of talks on turbulence, which is still remains very mysterious. Also, we had a talk on scalar shell collisions, essentially the collision term and when they can dominate. We had some great information on the bubble wall velocity, and also a nice talk on the hydrodynamics in particular, and the limitations of the bag model. And then perturbation theory and its limits of finite temperature and how to improve it. How to organize it consistently with dimensional reduction, and of course simulations. So perhaps it's perhaps unless someone has any burning question, and of course if you do, please feel to jump in. We can just go through the topics in that order and see who has, if there's anyone has a question or a comment or some topic for discussion. So perhaps let's begin with turbulence. We had multiple talks on that. Perhaps one of the most mysterious topics and least understood topics in this field. So if anyone has a question, feel free to raise your hand or leave some comment in the chat or a point of discussion. Someone privately asked me, what are the detection prospects for discerning whether you have a chiral phase transition signal? Yeah, how well can we? I don't know if anyone knows, but how well can we know whether we're seeing a chiral or non-chiral signal, which could be a result of turbulence?
Do you mean just chirality of the gravitational wave spectrum, or?
I guess so, yes, yes.
Oh, in that case, Alberto just published a paper on this, I believe.
Yes, sorry, I didn't understand well, yeah. So what is the question again? What would be the prospects of detecting such a...
Yeah, telling whether gravity... so I guess from the context of the question that seeing the chirality would be a bit of a smoking gun. Well, one of the contribute to a smoking gun that you have a turbulent signal. What are the prospects for seeing that this signal is indeed chiral, a chiral signal?
The original signal. Yeah. So I'm not an expert on this. I was mostly doing the simulations already, considering that we have a chiral magnetic effect. A chiral magnetic field, but there are some scenarios that maybe I had some slides on that maybe I can share.
Oh, sure.
On these different scenarios. Give me 1 second. Okay. So there's I was just doing some collection here, and we have the reference now in the paper, but there are some models that have been proposed in order to generate magnetic fields in this case. with helicity in order to then generate gravitational wave signals with chiral path. And some of them would be for so some of these productions would be via Farallon decay during the electroweak phase transition, for example. This was in these two papers by Tamai Vachaspati, which I think is here in the audience. He asked the question. And one of his models was producing these helical magnetic fields. Then there's also the generation of the Chern-Simons number through Arinan-Lepton anomalies, which was proposed by Cornwall, and then also some inhomogeneities in the Higgs field in some hybrid models of inflation, which has a preheating scale at the electroweak scale. Then on the other hand, if we have initially, so these are some of the models that can generate magnetic fields. We are not, in our simulations, we're not modeling any of these. We're already assuming that this magnetic field is there, and then we compute its dynamical evolution and its coupling with the velocity field and the generation of chiral gravitational waves in this case. And so it's okay. Yeah, also if there are magnetic fields already present that have been generated during inflation, then there are also some mechanisms to produce helical magnetic fields coming from inflation, as well as, for example, the interaction of axion fields with a magnetic field could generate helicity in the magnetic field. So these are some of the models that we were just considering for the justification of having possible helical magnetic fields.
On the subject of turbulence, I have a question which maybe the answer is simply we don't know yet, but it's generally assumed that the sound shell is in most cases going to dominate. Obviously, Marek talks about cases where you can get the collision term to dominate, and that the turbulence is going to be subdominant, perhaps except for in the UV. But this comes from a fairly arbitrary seeming guess of from the fact that we insert this epsilon, this efficiency factor of energy going into turbulence of about 5%. How much control do we have of that? Like, could that be an order of magnitude off, for example, and turbulence actually dominates maybe for some thermal parameters or maybe for most thermal parameters? Does anyone have a feeling of how well settled is it, the sound shell usually, the acoustic contribution usually dominates?
I think the kind of numerical prefactor before the shock formation time is still up for debate. I don't think beyond dimensional analysis we have a good feeling of how quickly you get it and then how much actually contributes. I think that's still an open question. Exactly how quickly it turns on and how much it contributes.
I think Daniel probably has some interesting things to say about how much turbulence is generated.
I mean, we did see that at least for the equation of state that we looked at, that for these slower deflagrations and potentially also hybrids, though we haven't actually published any data relating to that, so that's kind of preliminary work. But that there can be vorticity that's generated during the collision of bubbles. So that would actually almost seed kind of the precursor to turbulence with potentially quite a high, quite a high epsilon factor early on in the simulations, and actually you'd have coexisting kind of sound waves or longitudinal modes and vortical modes that could source at the same time. And I think the kind of long-lived consequences of that haven't really been properly studied with numerical simulations.
So in your simulations, the region of parameter space where you saw fairly dramatic suppression in your fluid velocity, I guess through this energy loss into vorticity, that could be a place where actually turbulence is heavily enhanced.
Yeah, definitely. Or
I think
yeah,
it's possible also that the vorticity there just does its thing and then goes away. I don't think we can tell from the simulations we've done whether it is going to give rise to turbulence or not. I think it's an interesting possibility, but I don't think we can say from what we have whether it does or not.
and I think we also haven't really, in the other scenario of fast moving hybrids or detonations, shown that this decay of sound waves, or decay of longitudinal modes into vortical modes, and then development and formation of turbulence has not really been done, and needs to be done.
If turbulence can dominate for deflagrations, that's a dramatically different power law, which would be a pretty interesting thing that we can get that information from any signal that we see.
Yeah, I guess for like very weak transitions, you wouldn't expect it to well, again, it depends on exactly how this decay of the sound waves and formation of turbulence happens, and how much of the kinetic energy is converted into turbulent kinetic energy. I think that still remains to be seen. But I think the point that Mark was commenting on is that that there's this larger muddying of the waters for if you have slow, or well, not even necessarily that slow, but if you have deflagrations that occur with these kind of intermediate to strong transition strengths of order, say 0.1 to 0.5, then you can produce substantial vorticity during the, immediately after the phase transition completes effectively, which would then substantially affect the, applying this sound shell model picture. And I think that needs studying both with numerical simulations and modeling.
I think that was the key. That was, I think, one of the things I was trying to. Sorry, Mark.
I just wanted to jump in and say I wouldn't want to give the impression that the turbulence ever dominated. I think there was ever a case where the kinetic energy in the vortical modes was larger than the compressional modes. But Daniel will has a better recollection of that.
I thought it was 50-50 in the worst case scenario. It was in that paper.
Yeah, I think it was close to 50-50. I need to check the actual data to.
Normally when I give talks like that, I include the plot which we made of that result. But today, of course, the one day I didn't do it. I can quickly check it now. But I think the other thing to bear in mind is that we haven't seen, for example, the formation of shocks in simulations yet, and in fact, we probably won't because of the difficulties we have there. But yeah, no, it's like so in the worst case scenario in this the paper, which is 1906 0040 paper that I cited in my talk, it can be order 1 the fraction in vorticity. If you look at like figure 1 in this paper, this plot, for example, this paper. So it can be a substantial fraction in vortical modes. But I really don't. I think I would not rush to conclusions that this is actually a direct progenitor of turbulent behavior.
And as Marek pointed out, it is probably quite difficult to obtain these slow-moving and also strong transitions.
I think I would like to ask Marek a question about that. So you cited a paper by Jim Klein. I just wondered which paper it was. I don't recall. I don't recall a paper saying that wall speeds were fast. So.
Where they did find, Jim Klein has been finding recently that baryogenesis doesn't just crash when you hit the speed of sound, but you have a gradual fall off. Actually, in fact, you get a maximum in the models he looked at for higher than the speed of sound, because you have two competing effects: the degradation, because you're going above the speed of sound, so you can't diffuse as much, but also you have less washout, I guess.
Yeah, maybe it's not completely obvious from that paper. Yes, let me find it. But essentially, we're also looking at that a bit, and it seems here the connection maybe isn't obvious, but it seems that the problem with observing, let's say, the cases in which the wall is actually stopped by the friction of the plasma is pretty much that the alpha is very small then. It's you really don't really get to 0.1 or so, and you're already at the Jouguet velocity. Yeah, but this is the paper. Yeah, but actually I wanted to ask you something, because in your results, there are no...
If you don't mind, there was a question in the chat first, but could we come back to your question maybe in about 2 minutes? But Chiara Caprini popped in a couple of minutes ago saying, I was wondering if whether there isn't an issue about the viscosity though. It's late here, sorry, my pronunciation. It seems to me that the viscosity is in the early universe is expected to be so much smaller than the one in simulations, isn't it? So I suppose either Daniel Cutting or Mark Honash or David Weir would be the optimal people to apply to that.
Yeah, I think this is an important point, and certainly in our simulations, we have a fairly naive way of discretizing the equations of motion, which helps us in some ways. It saves us from getting into some sticky spots, but in other ways, it does mean that we have effectively a relatively large viscosity induced due to the first order terms that we have in the evolution of the hydro. So that is true, I think. And we do, and but the things, of course, the hydro itself, without beyond the lattice, is scale invariant. So we can kind of extrapolate to larger volumes if necessary. Would you agree with that, Daniel?
Yeah, I think that's probably true. Like it should be checked how our results scale with viscosity, which at the moment is controlled via the lattice spacing because it's numerical viscosity. But yeah, also upgrading the order of the equations that we solve could also check that, and is probably something that we should check at some point.
So sorry to pile in on that question. So does that mean that this problem that the viscosity is too large is related to the problem that your lattice spacing is too large? And if you are able to take a continuum limit where everything works and the lattice spacing gets smaller and smaller, then you're also able to take the small viscosity limit.
I mean, in the case where you're looking at simulations of stuff which are kind of not occupying high wave numbers on the lattice, then the effect of the discretization as inducing a viscosity is very small and doesn't really. And on the time scales on which, for example, we've done the simulation so far, it's very small. But from the simulations that Chiara talks about, for example, this starts to become important because we want to try and get as much dynamic range as possible. We are trying to see if we can see some sort of cascade forming, and the only way we can get energy removed from the system is through lattice effects. Therefore, it doesn't induce a form of viscosity. And in the issue of, as you say, kind of finding a sense extrapolation becomes much more subtle and non-trivial, and that's one of the reasons why the work with Chiara has been so exciting, but also quite challenging. And there's been a lot for Daniel and Pierre to overcome when extending the code to cope with that.
Yeah, I guess it's the size of the lattice in comparison to the kind of the peak scale or the space that you have between that and the peak of your velocity power spectrum, which sets the kind of important relevance of the viscosity, I think. But again, it's something that we're kind of trying to understand better and improve currently and recently in the previous project.
And so I want to check Chiara Caprini if she had comment on the responses to her interesting question. Okay, so then perhaps let us return to Marek's question. If he
So I was
knows
just
what it
going
was.
to ask about hybrids, because, well, Daniel pointed out rightly that, well, those effects of suppression can be also important for hybrids, but you didn't have that in your results. So the question is why?
We haven't looked at them yet. We want to, but we just haven't had time. We will.
I think the answer in part is that we didn't have space in the PRL, and we were like, we'll save that for the longer paper, and then the longer paper has been delayed and delayed and delayed. So that's part of the answer. Because when talking about hybrids, I think it's kind of there's some other kind of interesting things about whether they appear or not. And in what circumstances you actually can find them, and finding them in these spherically expanding numerical simulations that we've done, rather than imposing a kind of fixed wall velocity and then solving the junction conditions. Their appearance has only been shown in a pretty small region of parameter space when you use the high temperature approximation. But it's kind of, so prior to this, it wouldn't have been possible to simulate them. But one thing that we found interesting is that you do see them when you switch to this bag equation of state in a wider region of parameter space. So we wanted to try and understand that a bit better before kind of discussing them in other works. But again, it's something that's on the list.
If anyone is a talented person working on bifurcation theory of partial differential equations, and they've got a few years to spare, they could look at whether hybrid solutions are attractive fixed points of the system of equations. I think the answer is interesting because it does seem to require fine tuning on the spherical case, whether you get them or not. So yeah, so there are
depending on your equation of state, which is weird. So.
But yeah, I think the short answer is we didn't have time, and there was enough fun stuff to talk about already.
Okay, but there is something non-trivial if it depends on the equation of state whether they appear at all or not.
Yeah. Maybe I'm advertising our preliminary results or ideas too much. Mark's smiling, which maybe means sharp.
If you do it, cite us. That's all we ask.
So one question, if we can move on to some of the other topics. The theoretical errors for perturbation theory were shown to be very, very large for your latent heat and for your percolation temperature, particularly with relevance to the Sancho model, calculating observables from the Sancho model. So I was curious, is there any reason to feel to know whether these would be just as important for say the bubble wall velocity, or for the collision term in the models which Marek was talking about? Like how broad a problem is this? Are these perturbation theory problems that we talked about, and have they been considered much for these other scenarios, like the bubble wall velocity and the collision term?
I guess, well, Jessica was saying how basically we need to get the leading order right before we can talk about next to leading order corrections with the bubble wall velocity.
mean, as far as I'm aware, sorry, could you repeat your question, Graham?
Yeah,
So
it's a
essentially
bit-
you're asking if non-perturbative effects could affect the bubble friction.
Essentially, because it affects the latent heat and the timescale by orders of magnitude. Could it affect essentially the friction and ultimately the bubble wall velocity by orders of magnitude?
It might. I mean, the regime, we're assuming the bubbles are moving relativistically, so the energy of the incoming particles is of order gamma t. So there's a kind of separation of scales, and also there's a separation of scales in that there's the kind of temperature effects which go like T, and then there's the kinematical effects which we're studying in the relativistic regime, which go like gamma T. So we don't take any of these thermal effects into account. And I mean, we do running coupling in the numerical simulation, but those couplings are all perturbative. I would think non-perturbative effects would not have a large impact on this part of the calculation, given the assumptions that the balls are moving relativistically and we have these separation of scales. However, maybe someone
from the equilibrium side, you'd expect stuff to be like perturbation theory to work worse when you have high occupations in some modes, as you have in the long wavelength modes.
Yeah, I mean, are you talking about Bose enhancement behind the wall or Fermi blocking behind the wall?
Yeah, well, the Bose side.
Yeah, we did not take those into account. Essentially, we assume like all the distribution functions are one pretty much. That's something we would want to do in future, but I feel like there are other issues we want to kind of address before that, which was maybe alluded to in the first session.
So you have soft bosons being created, right, at this bubble. So I guess depends how soft they are to some extent. If they're very soft, like some powers of G times T, then they might start to become non-perturbative.
Yeah, I agree with you. That's when thermal effects and these non-perturbative effects would become relevant. But at least from what we find, actually the most pressure comes from like a high KT, a high transverse momentum regime for those gauge boson emissions from the structure of our matrix element.
Okay, so yeah, it might be that the perturbative stuff is most important.
Yeah, but I agree with you. We're kind of relying on a good separation of scales, and this becomes worse and worse if you dial down the initial gamma T.
It could also be a different in relativistic and non-relativistic bubbles as well. So,
yeah, I mean, we're pretty much forgetting about finite density effects and these non-perturbative effects. And I feel like, I believe that's reasonable if you're in the relativistic regime.
If your bubble wall is really contracted and like, if all of your length scales of relevance are small and hence all of the like modes that are interesting are short wavelength, then I guess
exactly. I mean, one thing we want to do is look at finite width bubble walls, because something people are confused about is the mass independence of what we found. But that essentially comes about because the leading order interaction is the matrix element itself is independent of the mass. Like as long as a mass is acquired, there's an interaction. But this actually comes around from the assumption of the profile of the wall being a step function. So if you introduce some finite width, you now have an additional scale in the problem, which may affect the final pressure result. So this is something we want to explore, and maybe that would introduce, without having done the calculation, a kind of mass scale gamma squared temperature to which would be more in line with the results of Bugumila and collaborators.
I think this is kind of interesting because when we do like these field fluid simulations, the friction term we have is kind of like an expansion in terms of the gradients of like the wall, like so basically how the wall changes. And of course, Matt, it'd be interesting to kind of think, and we have thought a little bit about how we match those friction terms on to what's actually seen in the wall velocity calculations. So it's interesting to hear that you're also thinking about how to go to thicker walls, because it'd be interesting to match that onto the friction terms that we actually use in the simulations and see if it makes a difference.
All right, that's good. That's good to know.
So if I understood Carlos's talk correctly, then your Jessica's effect is coming from the deviation in equilibrium, and the effect in Bogomila's paper is actually coming from this entropy conserving effect. So would you even expect these two contributions to be similar?
If I may say something, I wouldn't, because as Jessica was saying, in the ultra-relativistic case, all particles get transmitted, and then the particle distribution functions don't have time to, if the wall is infinitely thin, they don't have time to adapt to the equilibrium distribution that would correspond to their acquired mass. So I think it is really a strongly out of equilibrium case. So I personally wouldn't expect that the two effects should agree necessarily. They are describing different regimes of physics, I would say.
And yeah, I agree. Like, because the effect in the equilibrium comes actually from having equilibrium distributions on both sides of the bubble. And in the case of ultra-relativistic bubbles, somehow this distribution is not equilibrium. You follow individual particles, so you cannot have equilibrium on both sides, and this really destroys this gamma squared scaling that we see. But on the other hand, you get a different source of gamma squared scaling, which is, I think interesting in itself. But I wouldn't expect to see a matching between the two gamma squared scaling.
Yeah, I mean, I think it's something we want to, if it's a coincidence, it's a coincidence, but it's something we certainly want to incorporate, this finite wall width, and see how that plays out. Because the analogy I made earlier, perhaps I didn't make it very well, is essentially we're treating this like a scattering, which we understand well how to do that. And the wall has some non-trivial form factor, and we've assumed a kind of given form factor given the step function. But if we have some width, there may not be support for very high momentum modes. Like, that may act as an additional cutoff.
Do you think you could model wall width effects with some sort of accumulation of scattering experiments, scattering in different regions of the wall, like divide the wall in regions of some width, and then try to see if you have scattering at every layer, and try to see what happens if you accumulate this effect over several layers or something like that?
Yeah, I think that's what we want to do, kind of use the same technique we were using before, which is this kind of vacuum persistence amplitude, but rather than kind of integrating over a finite width, integrating over an infinitely thin width, integrate over a finite width, and kind of see how the rescatterings can cause essentially some virtuality for the outgoing particle to shower. I mean, what I'm not super clear about is, like, we're, in our approach, we see lots of final states inside the bubble wall, because essentially the incoming energetic particle can interact with the bubble wall and be put off of its mass shell. I mean, I'm not sure exactly how to connect that with the equilibrium versus out of equilibrium effects. I don't know if you have.
No, I think, I mean, the equilibrium just means that a particle will have time to scatter with other particles many times while crossing the wall. And then
yeah, I suppose it doesn't
can,
because it's just super
exactly,
super hard.
It's when it's hard, maybe you get one scattering or with the wall itself, but not scattering in between the particles themselves, such that they cannot relax to equilibrium distributions while the wall passes. So I guess, you have interactions with the wall and then interactions among the particles themselves. And then in order to maintain equilibrium, you would have to, you need that the particles that are traversing to the wall keep interacting themselves such that they can reestablish equilibrium. And I guess if the wall is passing so quickly, you don't have time for this, I would say. Yeah.
We have a question from Anupam Mazumdar. How do you ascertain that you have reached both kinetic and chemical equilibrium? Especially if you have BSM interactions.
Well, you can do some back of the envelope estimates at least to see if it's reasonable. Just comparing the interaction rate between particles, including BSM if you want, to the time of passage from the valve wall. And then if the time scale associated with interaction rate is much smaller than the time of passage to the wall, it would be reasonable to expect that you can keep local equilibrium. Yeah, but it's still, it's not a proof, but it's just an argument on reasonable.
So I guess you compare an interaction timescale with, say, LW over VW.
Yeah, something like that, yeah.
There's a follow-up question. Thermalization is not a back of the envelope computation. You really need some strong type interactions, so maybe worth checking.
Yeah, I agree. I think it's a reasonable question to ask, for sure. Absolutely. I was just saying that I cannot do right now and give any better answer than a back of the envelope calculation.
I have a question, I guess, for Carlos and Bogomila about these solutions which maintain equilibrium. These hydrodynamic solutions which don't generate any entropy. So I just wondered how generic they are. Is this very, very special solutions, or should we expect to find them? I guess is my question.
Bogomila, do you want to jump first?
Well, I guess it's more a question to you because you had explicit solutions for those cases. We more assumed thermal equilibrium, and then you showed it's really possible. So please go ahead.
Yeah. So at least for deflagrations, my impression is that they are pretty generic because I could find very solutions easily. For detonations, I had to look a bit harder, just lower the number of scalar fields such that there's less interactions that can, less strong hydrodynamic effects. But my impression is that, for this, for the deflagrations, I don't think it's hard to find the solutions, and then they could be pretty common.
Does this mean that the entire transition stays at equilibrium, which would be that's kind of violates my intuitions about first.
I think that in a realistic setting, you would have to combine the effect of some degrees of freedom in equilibrium and some degrees of freedom possibly out of equilibrium. And then you would get an extra friction term in the equation of motion from the scalar field coming from out of equilibrium degrees of freedom. But you would still have this hydrodynamic effect from the field dependence of the enthalpy associated with equilibrated degrees of freedom. So I would agree with you that it's not reasonable to expect that all degrees of freedom, especially very massive ones, which acquire a large mass during the phase transition, I guess they won't stay in equilibrium, like, I mean, the top quark, for example, or something like that. And then, yeah, I think in principle, one should try to combine both. Yeah, but it's a good point.
Do you expect the two contributions to behave independently, such that you can just solve the two terms independently, or?
Somehow, I guess, since this hydrodynamic effect comes from field dependence of the enthalpy, you have to solve simultaneously the equations for the scalar field and the plasma, and then I don't think there would be a way around it. Yeah, I don't think that, yeah. I right now don't see an easy parameterization of saying, okay, if I solve only the equilibrium, what's the change of velocity coming from extra friction due to the non-equilibrated degrees of freedom? Yeah, I don't think it's an easy question to answer. Yeah. I would expect naively smaller wall speeds just because there's an extra source of friction, but that's all I can say.
So perhaps we can shift gears to the hydrodynamics. Of course, if anyone has a question about that, feel free to jump in. So I had a question about hydrodynamics. So I believe that simulations currently use a bag model. I believe I read that word in Cuttings. Is there any plans, or is it simple to implement some of this extensions to the bag to a bag model equation state?
Who are you directed at, ourselves or Alberto and collaborators?
So to basically anyone who's done a simulation using a bag model, or perhaps if they're already done beyond the bag model. I know the one example I know of is actually Cuttings' paper says Cuttings' paper explicitly on the vorticity effects, which I believe you also on, talks about say use a bag equation state, if I recall correctly.
Well, when I first wrote the codes to do these simulations back in 2013, we didn't use I didn't use the bag model there. I used just a simple kind of standard model effective field theory, just phi cubed phi to the fourth potential. The problem is that has some issues where basically you get when you do these simulations, we found out later that you end up getting kind of your speed of sound goes negative. It's basically the pressure behaves in an unexpected way. So we found we had to fix that basically in order to go to stronger transitions and explore the parameter space more effectively, because it was clearly a pathological equation of state that we were working with, which didn't function properly in certain regimes. And that's what led us to the bag model, because essentially you can kind of tune up the strength of the bag model arbitrarily. And that was one of the things that Daniel implemented for this vorticity paper.
Yeah, it turns out the high temperature approximation doesn't work at low temperatures.
Funny that.
But yeah, we'd like to extend it again. It's another thing that we want to do, either using one of these simple extensions or by actually using some kind of lookup table to put in a more realistic equation of state, or a more realistic potential rather. But again, just requires more coding and computer time and simulations and thought, and we haven't done it yet.
I'd like to say that my intuition would say that it shouldn't matter what the equation of state is, but the facts on the ground seem to suggest otherwise, although I'm not quite sure I understand why yet.
So that pathology, which David mentioned, Jorunde, I guess you didn't find that in any of the perturbative models, which you worked with, right?
Well, if you try to do high temperature effective field theory at low temperatures, then probably would. But maybe, yeah, sorry, I interrupted something.
Well, we also, I'm not sure if this is exactly the same effect, but we also saw that our speed of sound at lower temperature blows up because of a high temperature expansion breaking down, which wasn't relevant for our own computation, but I think we could sort of remove that weird behavior by putting some Boltzmann suppression by hand. This might be related, I think.
So can you explain where that comes from, Jorunde? Sorry, just trying to work it out. Cool.
If I recall correctly, it was so this model was a standard model plus a singlet, and we had for the thermal corrections we used the full J functions, but we also had the contribution from the daisies. So no full dimensional reduction, but the daisy terms, and in those terms you have thermal masses which are computed in the high temperature expansion. I think it was coming from there.
I think we were doing something a lot simpler, like we were using a polynomial form of the high temperature approximation to model the potential shape. So I think potentially, with a bunch of constants, and I think that was part of the issue, was that then when temperature gradients enter from these strong nonlinear transitions, you can really deviate a large way away from the critical temperature when you tune up the transition strength.
Yeah, the original motivation for this code in the 1990s was bubbles in potentially, well, actually also droplets, but potentially bubbles either in a QCD phase transition or later on in a potential first order phase transition with the actual Higgs field, before we found out later on when we discovered the Higgs that wasn't, or when we excluded it increasingly in the late 90s, that wasn't going to be a thing. So I think then people were thinking that's why the code I developed initially just used a very naive high temperature effective potential. And like I said, I'm very surprised that it matters, but it does seem to matter.
So, using the moment that we are quiet, I'm afraid we should be closing the official part. I'm sorry to finish the interesting discussion, but well, the room is open, so if someone can stay, you are all welcome. But if someone is busy with other stuff, then yeah, you can go, and see you tomorrow. Thanks.
Okay. I stop recording.
Thank you for an interesting day. I'm afraid